Hi everyone, I'm Felix. Today I'm going to present our work, A Formalism of DNN Accelerator Flexibility. DNN application are everywhere. As the quote from Andrew says, AI is the new electricity. To run this DNN model with runtime energy efficiency, people start to build specialized hardware for it, which we call DNN Accelerator. So why do we need a specialized DNN accelerator? Because DNN models are usually large, which often require millions of parameters, and the size actually grows with time. For example, the number of weights in AlexNet in 2012 is about 4 million. However, in 2019, Megatron has over 8 billion parameters. It also infers billion of computation, and we need lots of parallel compute. Second is that it also introduced heavy data movement across memory hierarchy. To reduce the energy of data movement becomes one critical issue. The need of parallel compute makes general purpose CPU inefficient, and the need of energy efficiency makes general purpose GPU inefficient. Now let's take a look at a template of a canonical DNN accelerator. First, it will usually house hundreds to thousands of parallel computation units. Then we will use what we call data flow or mapping to map the DNN computation onto it. Here we take a deeper look at what a DNN accelerator is made of. First, we'll have PE array. In each PE, there could be 1 to several ALU units. Second, we will have hierarchical buffer. For example, a small local scratchpad beside each PE, share global buffer and off-chip DRAM. Third, we need network on chip, NOC, to distribute and reduce data across the PE array. This forms the hardware design space. Also, we have mapping, which tells how the DNN workload are mapped onto the accelerator. It includes several components like tiling, ordering, parallelism, and shape, and we will go into detail later. This forms the map space. First, let's see how we can describe a mapping. In this work, we focus on interlayer mapping, where interlayer mapping, like fusion, is not considered. For example, to express the mapping of a convolution 2D, first, we have tiling. It is not likely we can fit the whole tensor on the on-chip buffer. Therefore, we will use tiling to move partial of the tensor on-chip. The tile size decision will dictate how efficient we utilize the buffer and compute. Second, ordering. The order we fetch and execute a tile is also important because it will dictate which dimension we utilize the most. For example, they are weight stationary, essentially keeping the weight at the outer loop and reusing the weight. Third, we have parallelism. We can choose to parallelize the compute across PE, and which dimension to parallelize can dictate the PE utilization. Lastly, we have logical mapping shape, or called level of tiling. It describes the number of tiling levels we use in this mapping. It will correspond to the buffer hierarchy, such as L1, L2, L3, and memory. It also describes the logical shape of the compute unit, like the 2D PE array shape of 16 cross 64. Finally, T for tiling, O for ordering, P for parallelism, and S for shape forms the 4 mapping assets of the DNN accelerator. Here we show some two examples to show you why mapping matters. First, tiling. For the simplicity, we will use gem workload and a 4x4 PE array as example. Here, A represents input, B represents weight, and we assume weight stationary, meaning we prefetch the weight and stream in the input. Now let's see what could we do for tiling. In option 1, you will tile A into 2 smaller tiles. In option 2, you choose to tile B into 2 smaller tiles. Let's see what's the performance implication. In option 1, the first half of B tile is prefetched and A tile 1 streaming. Then we fetch the second half of B tile and streaming A tile 1 again. And we repeat the same procedure for A tile 2. To summarize, P array utilization is about 100%, and both A and B are read from memory twice. In option 2, B tile 1 is fetched and the entire A tile streaming. Then we fetch B tile 2 and streaming A again. This utilization is still about 100%. However, we not only need to read B once. Then ordering. The option 1 could be as we used in the previous slide, weight stationary. Then A will be read and streaming twice. And option 2, if we change it to input stationary, then A is fetched and B stream in, then both A and B are read once. Then parallelism. In option 1, we can parallelize across these 2 dimensions, and the P utilization is about 50%. In option 2, we can parallelize across another 2 dimensions and yield 100% utilization. For logical mapping shape, in option 1, A is read and streaming twice, and array is 50% utilized. In option 2, if we can support a more flexible logical mapping shape, then we can fetch the second half of B to the lower half of P array. Then we could read A only once and multicast, and P is now 100% utilized. So to support this different mapping option, we actually need hardware to have flexibility. So what does it mean, flexibility in the DNN accelerator? The flexibility of the accelerator means the hardware and software support for running diverse mapping for the same workload. Mapping flexibility is quite useful because there are diversity in DNN models such as layer size, shape, and types. Also, there are diversity in workloads such as stepwise, pointwise convolution, or sparse workload. Essentially, more flexibility in hardware will allow more possible mapping and higher chance to find the optimal mapping in the snap space. However, flexibility comes with area and power costs. For example, to support tiling, one practical consideration is using hard partition input with output buffer or the soft partition one. Apparently, soft partition will have more flexibility, but also has higher complexity. Second, ordering. It will introduce a configurable address generator to dictate the order of buffer fetching. For parallelism, we need mask and sum control logic alongside PE to control spatial or temporal reduction. For shape, we need network on chip to support different ways of PE clustering. So we have introduced TOPS mapping axis, and to support or not support them, we can form a 60 different classes accelerator design space. While class 000 means no flexibility, and class 111 means all the TOPS are supported. So different accelerator pick to support different combination of mapping axes because they have different design budget and also because they target different workloads. Next, along each axis, we can choose to fully support it or partially support it or just become inflexible, stick to one mapping options. So the flexibility degree, we can make it to 0 to 1. And the flexibility degree here, we call it flexion. It means fraction of the supported map space. For example, to describe a tile flexible accelerator on resonant workload, we could say it like T-flex accelerator with 0.5 flexion on resonant workload. It means hardware has flexibility to support 80% of the tile size combination of resonant workload. So formally, the fraction is the supported map space over the entire map space. Here we show example of the entire map space of a layer in ResNet. Here the darker red means higher performance point. We can observe there are multiple higher performance regions which we circle in green. Now let's assume here we have a hardware with 0.5 flexion. Then what it means could be like this. The yellow part is the supported 50% of the map space. Potentially, the supported map space might not be large enough to cover some of the high performance region. Larger flexion has higher chance to cover high performance region. The performance of the supported region depends on the workload. The extreme case could be fully flexible. Then we are always sure we can always cover the best possible performance point. So increasing flexion could make the hardware to be more future-proofing. It means you can cope with more diverse DNN model. Let's see some evaluation. Here's the hardware resource configuration of the modeling accelerator. We performed two set of case studies. First is the discussion of fully flexible or partially flexible. And we evaluate using MNASNet workload and evaluate along each of the four mapping axes. In the case study, we want to show how the flexibility can benefit the accelerator to cope with a more diverse model. Here we show an interest case study of AlexNet accelerator. We investigate a what-if situation. So what if we added more flexibility into AlexNet accelerator 8 years ago, how would it perform for the new DNN workload nowadays? In terms of new DNN workload, we consider ResNet, MobileNet, and MNASNet, which are essentially more recent DNN convolution-based model. And also BERT, DLRM, NCF, which are mostly composed of fully connected layer. For the first case study, fully flexible, partially flexible versus inflexible. First of all, let me describe how we consider partially flexible in this case study. It supported some few selected combination of mapping. In the partially flexible accelerator, for tau, we consider equally hard partition input weight output buffer as partially flexible accelerator. For order, we only allow one type of order in each input weight and output stationary category. For parallelism, we only allow channel parallelism or activation parallelism. For shape, we only allow the P array to be logically partitioned with the coarse granularity of 16x16. So from this graph, we can see that the inflexible one accelerator is the blue bar, the green one is the fully flexible one. And we can see that when we are improving from inflexible to fully flexible, we have a very huge performance improvement. So as shown in this table, the tau is the most impactful axis to support. Also, from these two graphs, we can see that the orange bar and the green bar is very close to each other. So partially flexible, the orange bar on older axis and shape axis can give compatible performance to fully flexible, the green bar. In the second case study, we want to show how flexibility can help future proofing. We have two configurations of accelerator. AlexNet accelerator is accelerator specialized for AlexNet, and X model accelerator is accelerator specialized for X model. So for example, MNASNet model accelerator means an accelerator specialized for MNASNet. Here we show their normalized latency to run the DNN model, so the lower is the better. For example, the blue bar in MNASNet here means I take the exact AlexNet accelerator and directly run MNASNet on it without any tuning. What is the performance? And the orange bar means what if I completely redesign the accelerator to tailor for MNASNet? What is the best possible performance we can achieve? Apparently, the specialized accelerator, the orange bar, can achieve better performance than directly using AlexNet accelerator, the blue bar. And next, if we group the model by convolution-based and fully connected-based, we can see a clear trend of performance difference between convolution-based model and fully connected-based model. AlexNet accelerator, as an accelerator originally tailored for a convolution-based model, can perform relatively well across other convolution-based models as well. It is because there's some general mapping idea that is actually transferable between each convolution model. For example, the parallelism dimension choices and also the stationary choices. Now let's start to add flexibility into the AlexNet accelerator. For example, AlexNet T-flex means what if we add T-flexibility in the accelerator when we are designing AlexNet accelerator in 2014? First of all, given the buffer size number of processing elements, these are the area codes of each flexibility axis. One thing we can notice is that the additional area codes is not that affordable if we amortize to the cost of the entire accelerator. Then in the graph, we can see that the orange bar is always the lowest in the convolution model. It means adding tile flexibility can improve the performance the most in the convolution model. However, we can also observe adding tail flexibility to DLRM and NCF is not really helpful. It is because the performance is bottlenecked by suboptimal choices along other mapping assets like parallelism and shape. However, BERT can benefit from tiling. The key difference is that language model usually has higher dimension tensor and has more chances to leverage the parallelism strategy tailored for convolution model. And we can see that parallelism order flexibility is pretty helpful for DLRM and NCF. It is because these models are so different from convolution-based model to have flexibility to make different parallelism and order choices is essential. Therefore, parallelism and shape flexibility are impactful to be future-proof to new workloads. Next, let's add more flexibility into the AlexNet accelerator. We do this experiment in a sensitive analysis way, where we enable 3 out of 4 mapping assets to see how critical each mapping asset is. For example, AlexNet no T-flex means AlexNet accelerator with all mapping assets enabled except T-flexibility. First of all, the green bar here means we enable all axes, which is the most flexible option and will have the best performance. we can observe that the orange bar and the yellow bar are the highest for one and another model. It means the accelerator is more sensitive to tile and parallelism mapping axis. Also, we can observe gray bar is almost as low as green bar across all model. It means the older axis is the less sensitive. Also, to explain it another way is that proper combination of T and P and S can mostly compensate the lack of older flexibility. Therefore, we can say partially flexible accelerator can sometimes be competitive with fully flexible accelerator. Here are some takeaways. The additional area cost of flexibility is not as substantial when amortized to the cost of entire accelerator. Tile flexibility is the most critical mapping axis to support. Parallelism and shape flexibility are important to be future-proof to unknown new workload. Proper combination of TPS flexibility can often compensate the lack of older flexibility. Partially flexible accelerator with lower area cost can often achieve competitive performance to fully flexible accelerators. Conclusion: flexibility of hardware is often discussed in a vague manner. We define Flexion to represent the flexibility of DNN accelerator. Flexion indicates the fraction of supported map space to the entire map space. Flexion enables us to study DNN flexibility, impact, and trade-off in a systematic manner. We believe this will help both compiler, developer, and architect to systematically develop flexibility-aware accelerator design. Thank you.